Hi guys, sorry I abandoned you. I hope exam one went well. We're going to start this section, part 4, probability. This is where we start getting really mathy. So if you're not a math person, this will be potentially a struggle for you, but it's going to be the same types of questions again and again. So where exam 1, there was a lot of latitude in terms of what I could ask about and how I could combine all those concepts. Exam 2 tends to be much more straightforward in terms of the types of questions asked. So the content's a little harder, but the ability for me to think outside the box and do some crazy questions is a little more limited. So should in some ways be easier. Anyways, probability is the foundation for all inferential statistics, as you kind of saw with that lady in the smelling Parkinson's example. We were looking at the probability of getting out smelling 11 or more shirts if we were just guessing. So this understanding of probability is important for the inferential statistics side of things, even though it's sort of a bit of a step away from statistics and into real math for a little bit. So that's it. We'll start with part 4, and I'll make myself go away. Oh, that's the opposite of going away. All right, so part 4. We got our learning goals, and then we have a nice little introduction to probability. So you start with a definition of probability. Probability is just the odds of something random occurring. This is important because later on we will talk about confidence intervals where we're not talking about a random thing happening. We have some definitions to get started with. Anytime we do something random, we'll be looking at a trial or an experiment, which will generate an outcome, and the set of all possible outcomes is our sample space. We will be dealing a lot with these events, which we'll denote with capital letters, and then we'll have this notation. Probability of A is a probability of event A occurring. So the one thing I want to say about this is when we say like this, probability of, so in this case, something like the probability of more than or equal to 11 shirts, like we did in the smelling Parkinson's example, this is going to equal some number. So for us, it was something very, very small. We never are going to write the probability itself inside of the notation. This is what our probability of what. So whatever we're looking for, our event, is what goes inside the parentheses, and that just equals a number. We're never going to put the number inside of that notation. That's a very common mistake students make. All right, so our first exercise to sort of illustrate some of these ideas and definitions. If you're rolling 2 dice, you have a sample space of every possible outcome. So you can see them here. There are 36 possible things that can happen inside of that sample space when we're rolling 2 dice. And this whole thing is S. And we'll usually use this curly key bracket notation whenever we're writing out a set or a list of things. So then we have our first 2 events. Event A is rolling 2 dice whose values sum to 7. So A equals, and then we could write down the list of all possible outcomes that end up with a sum of 7. So we can look over here. We have all of this diagonal are ways to roll a 7 with 2 dice. So we have, let's just make this 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. So I want you guys to go ahead and do the same thing for event B, and then we'll come back and check. So B, rolling doubles, you can see. And then we can also do the same thing for C. Again, if you want, you could pause it. I'll pause it and just restart it so that way you don't have to watch me write a whole bunch of. For C, we only have 3 possible ways to roll 2 dice who sum to 10. All right, so there's 3 types of probability. We have the classic approach to probability. That's what this part is all about, part 4. So if we're talking about the probability of an event, this is just how many ways A can happen over how many ways the entire outcomes could go, right? So all the things in the sample space. So this is only useful, though, a big note to you guys, only useful when our outcomes are equally likely. So if we don't have something that's equally likely, you cannot use this approach. So this would not apply for our exams because I have true-false questions. Some of my multiple choice have 4 options, some have 5. And so this is not always the same in terms of equal likelihood. All right, sorry, he's being super noisy. So example 1. Is the classic approach of probability appropriate for the dice rolling? Well, that makes it pretty easy. And this is because all of the outcomes that we saw in our sample space are equally likely. Why are you fussing? All right, and so if we went to find our different probabilities, by the classic approach, this is just how many things fell into each of those different event spaces. So there were 6 ways to roll a 7 out of 36 different possible outcomes in the sample space. There were 6 ways to roll doubles out of, again, 36 possible outcomes. And there were 3 ways to roll a 10 out of 36 possible outcomes. And this is not a math class, so I do not care about making these into simplest fractions or any of that. I just want us to see this classic approach. The second type of probability is an empirical probability, and this is going to be at the heart of what we're doing for a lot of our inference examples, especially what we did in that smelling Parkinson's example, right? So if we don't know all the different outcomes, or if there isn't a set number of outcomes, what we can do is we can just do a bunch of different trials and then see how many times A occurs. It's exactly what we did with the smelling Parkinson's activity. We smelled those 12 shirts, we guessed, and we saw how often someone got 11 or more out of all the number of trials that we did. And then we used StatCrunch to generate even more trials. So we could see that that probability was very, very low. And here you have a nice little graphic to demonstrate that. Sort of shows you that the reason this is so useful, empirical probability, and why we can leverage it in statistics is this law of large numbers, which essentially says that as you take a larger and larger sample size, you will start to begin to approach the true value. So in this case, we're looking at the average percent of heads. So if we're flipping a fair coin, should be 50%. After one trial, it looks like the person got heads. So if they're using the frequentist approach, their probability of heads is 1 out of the 1 time. So they're guessing that this coin only shows heads on it. Then they did it again. It looks like this time they got tails. They had a 1 out of 2. And then up and down, up and down. You can see right around 100, even before 100, it's starting to level off. And it's very hard to get away from that 0.5. And that's something we're going to be leveraging a lot as we move into inference in part 6 and part 7. All right, the last type of probability is a subjective approach to probability. This is just based on your beliefs and what information you have. So something like, what is the probability the Chargers will make the playoffs for next season? That is something you can only do subjectively, right? You can sit there and say, well, they made it this far this season. You can talk about who's on the team. I have no idea. So you can just make up whatever the heck you want for this value based on your beliefs. And we'll probably all have very different values here.